Here are the governing equations for the unsteady flow. The equation for the stream function in log polar coordinates. So we have something that looks like the Laplacian in Cartesian coordinates. We have these extra exponential factors. We have a time derivative for the scalar vorticity. We have the Reynolds number showing up in the denominator here. Again, something that looks like a Laplacian in the vorticity equation. And then we have this nonlinear term here. So we want to convert these now to equations on our finite difference grid. We're going to use second order approximations for all the derivatives. So let's start with the stream function equation. You should know how to write down the second order method for the Laplacian. So that will give us, because we have a minus sign here, we have 4 psi I comma j minus psi I plus 1 comma j minus psi I minus 1 comma j minus psi I j plus 1 minus psi I j minus 1. That's this term, and that's equal to the right-hand side. So this term also division by h squared. So we multiply through by h squared. So we have an h squared e to the 2 psi I, and then omega on at the ij point. Okay? So that's the discretization of the stream function equation. This will be a matrix equation. We'll use a direct method to solve it. Now we want to discretize the vorticity equation. So the partial derivative of omega with respect to time will then become a regular derivative at the ij value of the grid. So d omega ij dt. And then we have this term here. So we have the Laplacian here, which will be 1 over h squared. So we have a 2 e to the minus 2 psi I over h squared times the Reynolds number. And this term here then will be the same as here, but with a minus sign. So it will be omega I plus 1 j plus omega I minus 1 j plus omega I j plus 1 plus omega I j minus 1. And then we have a minus 4 omega I j. Okay, so that's this Laplacian-like operator. And then we have this term here. So each of these center difference schemes for the derivatives will have the difference, center difference divided by 2h. So we'll have a 2h here and a 2h here in the denominator. So that's a 4h squared. So then we have a plus e to the minus 2 psi I over 4h squared. And all that factor multiplies these products of derivatives. So these are center differences. So the derivative of psi then will be psi I plus 1 j minus psi I minus 1 j. The derivative of omega will be omega I j plus 1 minus omega I j minus 1. That's the derivative with respect to theta, minus then the derivative of psi with respect to theta. So that will be psi I j plus 1 minus psi I j minus 1. And then the derivative of omega with respect to psi. So that will be omega I plus 1 j minus omega I minus 1 j. and then we close the bracket. Okay? So that should be the correct finite difference approximations. So let me summarize. In this video, then, I'm converting our PDE, coupled PDEs, to differential equations on our grid. We have the first PDE just converts to a matrix equation for psi, given if we know omega. And the second PDE then converts to a system of ordinary differential equations for omega on the grid, using the spatial finite difference approximation for the spatial derivatives. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.